Very good morning. Today, 28th May 2021. Our first speaker, Dr. Palsan Sannasi Abdullah from University Malaysia, Kelantan. He is well known for nanotechnology here, and then he is going to deliver a talk on synthesizing nanomagnetic adsorbent composites from Agrobiomass Residues, consumer and industrial prospects. Welcome you, sir. Please deliver your talk.
Good day. Greetings from Malaysia. I'm Palsan from the Faculty of Agrobiomass Industry, University Malaysia, Kelantan, Jeli campus. A virtual welcome to all for our sharing on agrobiomass-based nanomagnetic adsorbent composites. Firstly, a big thanks to Prof. Sanam and his team from the Department of Botany, SW University for organizing this wonderful, informative webinar. Our research sharing will be on some insights into synthesis, benefits, potential applications, challenges, and plan ahead. To start, let's look at some background information. What triggered the interest and the motive of this initiative? We've listed four main concerns here. In the local context, almost 70% of the water is sourced from groundwater. Ineffectiveness of filtration and clarification processes at water treatment plants lead to high turbidity and increased chemicals usage. This is more pronounced with normal filtration employing polymer media when turbidity is more than 20 NTU, as observed with groundwater. Polyaluminum chloride is used as substitute to alum and ferrous sulfate for potable water clarification. However, the higher quantity of polyaluminum chloride required can become very costly, can blind sand filters, and have very narrow range of effective dose. Mixed waste and colored effluent released by cottage industries showed lower complying rate to environmental quality standards, and existing treatment methods, if any, are either non-accessible, too expensive, or too technical, thus becoming less practical. On the other hand, the high use of chemicals, flocculating agents, and other absorbents usually leads to heavy sludge generation, hence higher incidence of secondary pollution, and sludge may be flushed into the waterways. Now, coming to our main player. Of the 1.2 million metric tons of agro waste produced locally and 1.7 billion metric tons globally, over 70% are left to rot and disposed as trash. Well, isn't that a waste being wasted? More than often, cleaning up means to gather all, pile up, and carry out open burning. This leads to air, soil, and water pollution, adverse health effects, and further deteriorates environmental and aesthetic quality. The vast development in the field of nanotechnology and applications of nanomaterials have been widely discussed in recent years. We know nanoparticle use offers many benefits and advantages due to its unique size and physico-chemical properties. And surely, nanotechnology has been the buzzword within many industries ranging from biomedical and pharmaceutical, health and medicine, biomaterials and advanced materials, electronics, robotics, and even clothing. Our areas of interest and its role in current scenario fall within potential applications in environmental, soil and agriculture, and personal care. For example, water consumption has increased for both consumer and industry. Water security is of concern not only in terms of quantity but quality of surface groundwater resources. Alternative approaches in water and wastewater treatment and when dealing with mixed waste is of importance for both users and water solution providers. Water treatment facility operators are also looking at alternatives for both clarification and filtration. Aluminium-based coagulants are becoming costly and sensitive on working pH and temperature. Though most work with nanomaterials are being directed towards biomedical applications, nanomaterials have also been suggested as efficient, cost-effective and environmental friendly alternative to existing adsorbent material for environmental remediation. Many reports on the use of nanoparticles like titanium dioxide, silica, silver, and even iron oxide itself are available in the literature. However, the use of nanoparticles in its free form in the open environment may not be the best approach. It will be difficult to recover the spent or used nanoadsorbent material, and it's not going to be feasible to remove nanoparticles by filtration or centrifugation. Magnet separation techniques have received considerable attention to address the separation problem. It can be employed in two ways. First, separation of magnetic target by an external magnetic field, and secondly, separation of non-magnetic targets such as organic compounds through formation of a complex with magnetic particle which is then separated by an external magnetic field. This is certainly a better option as opposed to non-magnetic nanoparticles. Amongst materials with magnetic properties, iron oxide nanoparticles are the most suitable for various applications, including environmental, and generally regarded as safe. The nanostructure is based on the common inorganic core of iron oxides such as hematite, magnetite, and megamite that have been the subject of intensive studies over the years. The three major iron oxide crystallite structures, namely hematite, magnetite, and megamite, and the placement of iron 2+, iron 3+, and oxygen 2- can be seen here. So, wouldn't it be advantageous to use iron oxide magnetic nanoparticles where one can recover the iron oxide with an external magnetic field? However, iron oxide magnetic nanoparticles have large surface-to-volume ratio and possess high surface energies. Coupled with high chemical activity, they are easily oxidized in air, especially magnetite, generally resulting in loss of magnetism and dispersibility. Due to this, stability issues are of concern when it comes to application, especially in solution like in water treatment. As such, iron oxide magnetic nanoparticles tend to aggregate to minimize the surface energies when dispersed in solutions, also sensitive to surroundings conditions like acidity. Competitive adsorption due to self-aggregation of iron oxide nanoparticles cause colloidal instability. Agglomeration makes separation difficult. Depending on the ultimate purpose of use, magnetic nanoparticles on their own are less suitable as adsorbents. These are clear limitations of using iron oxide magnetic nanoparticles in its free form. In order to optimize the synthesis of iron oxide nanomaterials in larger volumes, surface modification and medium modification are required. This modification could help produce stable magnetic nanoparticles which can resist oxidation and prevent self-aggregation. Thus, the need to develop a composite to explore, to find, and to have an organic platform to attach the iron oxide magnetic nanoparticles. Sharing some common sites of agrobiomass or agro-waste and their disposal. Here we can observe a stretch of coconut shells, husk being burnt openly. These materials can be of value. With coconut shell, durian husk, sugarcane bagasse, and many more agrobiomass residues. This will be our raw material source for biocarbon, obtained through thermal conversion by carbonization using top-lead updraft carbonization drum. This essentially is a much cleaner process that prevents the release of toxic gases and compounds. Biocarbon is carbon-rich, porous product with advantageous physico-chemical properties produced relatively at a lower cost. Activation, if needed, was performed by boiling biocarbon in aqueous salt solution. Use of nitrogen or steam for activation was not required. The surface modified biocarbon derived from agro-waste residues provide the much needed organic platform base. The biocarbon allows the attachment and binding of iron oxide magnetic nanoparticles. It functions as the backbone to stabilize the magnetic nanoparticles and provides structural frame for mechanical and properties support. Importantly, biocarbon holds excellent absorption ability. If the technology can combine the advantages of cheap biocarbon and magnetic particles to fabricate new composite material with high surface area, appropriate pore size, and magnetic separability, a promising normal adsorbent may be possible to be conceived. Much interest has since been towards the synthesis and use of magnetic nanoparticle composites. We focus on agrobiomass-derived nanomagnetic adsorbent composites. The material is a combination of biocarbon generated from agrobiomass, like sugarcane bagasse, coconut shell, as the medium, which was then modified with iron oxide magnetic nanoparticles. Nanomagnetic adsorbent composite, or NMACOM, is composed of two main components: a mix of agrobiomass-derived biocarbon, the anchor, the main bulk of the composite, and is complemented with iron oxide magnetic nanoparticles. The attachment of the iron oxide magnetic nanoparticles give rise to the functional nanomagnetic adsorbent composite. Now, moving on to synthesis, there are actually many reported works on iron oxide magnetic nanoparticles preparation and synthesis. This includes microemulsion, thermal decomposition, hydrothermal synthesis, and co-precipitation, among others. As one convenient and cheap method, co-precipitation has the potential to meet the increasing demand for direct preparation of well-dispersed water-based iron oxide nanoparticles. This approach offers a low-temperature alternative in the production of nanoparticles and better size control. Now, synthesis of our nanomagnetic adsorbent composite was achieved through co-precipitation coupled carbonomagnetization method. The whole process actually can be done in a single stepwise procedure in open environment conditions. Simply put, this is a surface modification procedure where we allow the binding and attachment of iron oxide magnetic nanoparticles onto the biocarbon. The initial synthesis involved co-precipitation of the iron salts in aqueous solution under mechanical stirring. Ammonium hydroxide or sodium hydroxide can be used as the reducing agent, followed by a series of temperature and time-dependent sequential heating and mixing, ranging from 30 degrees Celsius to 80 degrees Celsius. Biocarbon was added in the range of 3 to 5% weight by volume and mixed completely. The suggested particle size for the biocarbon is up to 300 microns. This is also dependent actually on the proposed final application use. Commercial activated carbon can also be used if preferred to substitute the self-prepared agrobiomass-derived biocarbon. Stabilizers are optional but preferable, especially for large volume synthesis as to prevent aggregation. Our choices include cross-linkers or surfactants such as epichlorohydrin, sodium dodecyl sulfate, citric acid, dimeticon, cetyl methyl ammonium bromide, and cyclopentasiloxane. This was followed by sonication before separation of the precipitate, which was washed and collected via an external magnetic field. The biocarbon held the magnetic nanoparticles in place, and importantly, no ion leaching was observed before or after use. Apart from the biocarbon particle size range, the other main factors that can affect the synthesis procedure are pH, temperature, agitation speed, and residence or curing time. The pH range during the synthesis of iron oxide magnetic nanoparticles is usually around pH 8 to 11. The effect of pH on the average particle size of the magnetic nanoparticles can be estimated from the Scherrer equation of the X-ray diffraction peaks. Increasing temperature can also affect particle size distribution and polydispersity. Particle size decreased with increasing stirring or agitation rate. Particles disperse into smaller droplets. Higher agitation reduced growth kinetics, resulting in smaller sized particles. Sonication is suggested especially when dealing with large reaction volume. The larger particles can also be obtained by aggregation of the small crystallites. Example of XRD spectrum for sugarcane bagasse derived nanomagnetic adsorbent composite is shown here. The iron oxide nanoparticles were in the form of megamite. The sizes of the nanoparticles can be estimated from the XRD data using the Scherrer equation, which gives a relationship between particle size and peak broadening by the given equation, where d is the particle size of the crystal, k is the Scherrer constant, lambda is the X-ray wavelength, beta is the line broadening in radian obtained from the full width at half maximum, and theta is the Bragg diffraction angle of the XRD diffraction patterns. EDX analysis also revealed the major constituent peaks for carbon, oxygen, and iron. Significant advantages of composite material can be summarized to the following features. It can be seen that magnetic properties enhance clarification, filtration and removal of pollutants from water and wastewater. It can be multi-waste oriented, effective for the removal of both inorganics and organics. Absorption process is rapid due to nanoparticle coated modified surface, where absorption and separation time can be reduced by 80 to 90%, minutes versus hours with conventional agents. Magnetic biocarbon can then be conveniently separated by use of external magnetic field, hence ease after use separation or recovery of spent material. And the material is reusable up to 3 to 5 cycles with more than 80% effectiveness retained with material recovery option. Up close with the hybrid composite material, responsiveness to external magnetic field was observed, indicating superparamagnetism characteristic. Now, let's see the consumer industry's prospects. For water solution providers, we propose an all-in-one approach as opposed to individual treatment processes encompassing of flocculation, coagulation, filtration, and absorption using ACH, PAC, alum, or activated carbon. The use of nanomagnetic adsorbent composite as clarifying and filtering agent is foreseen to ease turbidity and sludge issues by facilitating coagulation and separation of spent material. Now, to support our cause, we got the opportunity to meet our local water treatment provider at the treatment plant. Importantly, the chance to carry out a live demo on-site with real water sample, real time. Do note, the nanomagnetic adsorbent composites and the samples were used as it is. No prior filtration, pH, ionic strength, or temperature adjustments were made, and no additives, accelerants, or catalysts were added. There you go. Almost immediate. Now, let's see that again. Two nanomagnetic adsorbent composites of different particle sizes were used here for demonstration purposes. The spent composite can now be separated from the clear water and recovered with an external magnet for subsequent use. One of our team's achievements bagging the Grand Winner Award at Techplan Demo Day for the Nanomagnetic Adsorbent Composite, a gold medal for our Nanomagnetic Biocarbon Absorbent Composite product at the Nuremberg International Trade Fair, Germany. Here, the product also received interest from foreign water and wastewater treatment solution providers. However, we were not ready for commercialization as we haven't gone into mass production. My active fill, an active filtering unit fabricated for a local textile operator for effluent treatment. This uses a mix of nanomagnetic biocarbon composite and activated carbon as its filtering matrix. Effluent readings showed that COD, BOD, TSS, TDS, metals, inorganics, and conductivity decreased by 63 to 87% and adhered to local environmental quality limits. My MagniFill, a consumer-centric magnetic filter unit prototype for use with nanomagnetic adsorbent composites to be fixed at point of use or point of entry. As opposed to small amounts of nanomagnetic particles usually used for applications in biomedical and clinical field, a single environmental application run itself may require the material in kilograms, if not tons, to sustain the operation. Yes, this is good business, no doubt. But the biggest challenge would be to mimic laboratory preparation for mass production. We need to scale up the synthesis and surface functionalization of agrobiomass residues with iron oxide magnetic nanoparticles. Production conformity will be dependent upon technical matters which will determine the outcome of the final product in terms of size, shape, stability, and dispersibility, which will then dictate product functionality. Last year, we managed to carry out a trial production run. We made do with available equipment, mixing tanks, sonicator, and a double-jacketed reactor in batch mode. Production capacity was in the range of 100 to 120 liters per batch. We learned many things though. Much needs to be improved before a pilot production can be set up. Yield obtained was around 78 to 82% up to 6 kg per batch. It is essential to enhance the dispersion of the nanoparticles, prevent interparticles aggregation, and allow maximum concentration of the iron oxide magnetic nanoparticles to be in contact and attached to the biocarbon. All in all, we foresee a bright future ahead in the use of agrobiomass residues as the solvent precursor medium in the form of modified biocarbon to produce nanomagnetic adsorbent composite. This could actually solve agro-waste disposal problem. In addition, it is also expected to increase effectiveness and reduce operating costs of water purification and treatment and open up new areas for added value product development. We plan to mass produce nanomagnetic adsorbent composite for commercial application while making it a part of community-driven initiative for their socio-economic empowerment. Secondly, to develop affordable and competitive filter units for consumer industry use, and to tap onto various potential fields such as energy production and storage. Future collaborations are most welcomed. The use of nanomagnetic adsorbent composite for aquaculture and soil rejuvenation are also being explored as well. Iron oxides are considered to be safe for use in cosmetics and personal care products because they are non-toxic and non-allergenic. Iron oxides are even well tolerated by those with sensitive skin. Here, we incorporate nanomagnetic in masker formulations to take up the anti-pollution skincare theme. With that, thank you all for your kind attention. And again, thank you, Prof. Sudha, for this wonderful initiative. Till we meet again.